So in the last video, we talked about what the first derivative really meant graphically. We were looking at things like slope, right? So we were talking about if the slope is positive, that means our function is increasing. Or if we could say the first derivative was positive, that means our function is increasing. And if the first derivative is negative, our function is decreasing, and that kind of stuff. We were able to find maximums and minimums using the first derivative test, that sign chart for it, and everything was great. We also talked briefly at the very beginning of that video about how the second derivative is really just the derivative of the derivative, or we'll say it's the derivative of the first derivative. So finding the second derivative isn't that bad. It's not going to be that hard, except when we have to use things like the quotient rule and the chain rule again. So we'll still have to keep an eye out for those differentiation rules. But outside of stuff that we already know, it's not going to be terribly hard to find the second derivative, but interpreting it is going to be a little bit different. So what I want to do is focus really briefly on these two graphs here, and I want to talk about the differences between them. That's going to help us come up with what the second derivative is doing. The first thing that I want us to notice is that both of these functions, both of these graphs are increasing. That means from the interval from 0 up to 1 on both of these things, our first derivative is positive. So maybe I'll say that for both of these things. The first derivative is greater than 0. What that means is that if we draw any sort of tangent line on here, we could pick a point and draw a tangent line. Maybe I'll draw one there, or I'll draw one right around there, or we can draw one later on if you want. Or over on this one, we can draw one here. There's a pretty good tangent line, and oh, that's not a very good one. I missed it. We'll draw one. That's kind of hard to do. Right there, approximately. We've got these tangent lines on here. Maybe I'll put one more. Something like that. Notice that the slopes on all of these tangent lines are positive. They're all moving up and to the right. So what that means is that if we found the derivative at like a point right here, or a point right here, or a point right here, and on this other graph, here and here, the derivatives are positive. So that's how we could tell that the first derivative is greater than 0 on both of these things. Cool. What I want to look at is what's different about these two graphs. And the first thing that you could point out is that the curvature is different. They curve in different directions, right? This one kind of is curving in this kind of direction, and this one looks like it's slowing down and leveling off a little bit. Our intuition on that is pretty good. What I want us to do is to focus on what these tangent lines are doing, what the slopes of these tangent lines are. If we had to like pick some numbers to assign to these, we'd notice that the slopes, the actual number of what that first derivative would be here, starts off small, gets a bit bigger, because the slope is a bit steeper. So maybe this slope is like a half, and this slope is like, I don't know, 2. And then this slope is even steeper, meaning the actual number for the slope is even bigger. So what we can say is that the slopes get bigger, or what we can say is that the slopes are increasing. We'll talk about what that means in a second. Over here, notice that this one is the steepest out of the two, and this slope is pretty small. So as we move from left to right, here our slopes are getting smaller, which means our slopes are decreasing. So let's think about what's going on here. We're talking about things that are changing, but the things that are changing are the actual slopes of our function, not the y values. So when we think about rates of change, any sort of change on here, we should be thinking about derivatives, but now it's not the function that's changing, it's the derivative that's changing. So right now we're talking about the rate of change of a derivative, or we're talking about the derivative of a derivative. If the first derivative here, the slope, is increasing, that means that the derivative of this derivative is positive. You follow that? Let me try it again. If the slopes are increasing, that means the derivative of the slopes is positive. Since this slope is the first derivative, that means that the second derivative is positive. And over here, since the slopes, again, the derivatives are decreasing. They're getting smaller. That means the derivative of the derivative is negative because our first derivative is decreasing. Very weird. We call this concavity. So here we've got this positive second derivative. Here we've got this negative second derivative. And we're going to talk about concavity of a function. So here's our definition of concavity. The graph of a function is concave up on the interval a, b if the first derivative is increasing, the slopes are increasing, which means that the second derivative is greater than 0. Similarly, it's concave down when the first derivative or the slopes are decreasing, which means that the second derivative is less than 0. So there's lots of different pictures that we can draw. There are these two pictures. So I'll draw these two things as well. Maybe I'll draw my concave up in green. And so we have this kind of a concave up picture, and we have this kind of a concave down picture. Notice that for both of these, our first derivative was positive. These are both increasing functions. We could also draw something that's concave up but decreasing. If it's concave up but decreasing, it's going to end up looking like this. And if it's concave down but decreasing, it's going to kind of look like this. There are a couple of different ways of telling, I think. The first is to just draw tangent lines and see what's happening. If we draw tangent lines on this one, just like we had earlier, notice that the tangent lines are getting steeper in the positive direction. The numbers themselves are getting bigger. Notice here, the slopes, these tangent lines, are getting less steep, but they're negative. So this is really, really, really negative, and this is less negative. So if we're starting below 0, we're actually starting really, really far down, and we're getting up closer to it. So both of these, our slopes are increasing. Here, just like we drew before, we've got a nice positive slope that's getting smaller. Here, we've got negative slopes that are also getting smaller, meaning they're getting more negative. So again, our slopes are decreasing. So you can always try and draw tangent lines and see what's happening there, but you might notice something else. On the concave up spot, the tangent lines are all below the graph. Or you could say the graph is above the tangent lines. Same thing here. See how these are below the graph, or your graph sits just above these tangent lines? You could say if the graph is above the tangent lines, it's concave up. And if the graph is below the tangent lines, or if the tangent lines sit on top of the graph, it's concave down. So that works too. I look at tangent lines sometimes if I get really tricked out or have a hard time visualizing what's going on or anything like that. Another thing that you can do is notice that if you take these two pictures and put them together, you get something like this. So we could say that this is concave up like a cup. This kind of looks like the cross section of a little cup here. Something like that. Here's our handle. That's our little teacup here. So this is up like a cup. And over here, if you put these two things together, it looks like this. And we can say this is concave down like a frown. There's our little frowny face there. So anything that looks like it's a piece of a cup is concave up. Anything looks like it's a piece of a frown is concave down. Honestly, what I've always looked at is just parabolas. This is an upwards facing parabola, so it's concave up. This is a downwards facing parabola, so it's concave down. So I'll try and look at pictures of graphs and see if I can find where we've got nice parabolas that are either pointing up or down. So let me clear all this stuff out. And I'm going to draw a graph, and we'll just start labeling where it's concave up or down. So I'm not even going to worry about my axes or anything like that, but here we go. So you know what I should have done? I'm going to do this in black. Whoops. So that I can label my concave up in green and my concave down in blue. No, I don't want an axis. So here's my graph. Something like that. All right, so let's do all the, well, let's just start from the left. Here, if we kind of trace along our graph, see how there's a downwards facing parabola type look here? That means this whole section is concave down. But then at some point in here, it switches, right? Because see how there's like an upwards facing parabola here? So somewhere in here, we switch from concave down to concave up. It's a little tricky to tell exactly where that is. Similarly, again, we switch back to concave down here. We've got this nice downwards facing parabola. And then eventually, we switch to up again. Now, it's hard to find the points at which we switch concavity. They're somewhere in here. They're difficult to eyeball. I might go ahead and like put one right there, put another one, I don't know, maybe there. It's kind of hard to tell. And since my graphs are really bulky here, or bumpy, it's kind of difficult to see. But I might say these are the points where we switch from concave down to concave up, and then from concave up to concave down, and from concave down to concave up. Visualizing concavity, I think, is tricky to get used to. But again, you could always just draw a tangent line and say, oh, look, the graph is below the tangent line, so this is concave down. Or here, the graph is above the tangent line, so that's concave up. So keep an eye out for those types of things. Inflection points. These are those points that we just labeled. Those are the points at which the concavity changes, or what we'll notice is that the second derivative is going to change sign. So if we go back here, see how we go from concave down, maybe I'll label that in blue, CD for concave down, up to CU for concave up. That means this red point is an inflection point. Similarly, we go from concave up to concave down, so this red point is also an inflection point. And then we go from concave down to concave up, and so that red point is an inflection point. Notice that we don't really make a distinction between the first two here. This one goes from concave down to concave up. Over here, we go from concave up to concave down. We're not going to call them different types of inflection points because it's kind of hard to tell the difference just by looking at it. So we're just going to call these things inflection points, no matter which way the concavity changes. If it goes from up to down or down to up, it doesn't really matter. It's going to be an inflection point. Since we're talking about the second derivative changing sign, that means the second derivative is going from either positive to negative or from negative to positive. So that's what these inflection points are. Note that they have to be a point on the graph. So that means that the x value is in the domain of f. Just like we had with critical points and maximums and minimums, those have to actually be points on the graph. So we're going to be checking these in the domain of our function here. So again, if we went ahead and drew a picture like this, we could go ahead and say there's probably an inflection point right around here where it changes from concave down to concave up. There might be another one here where it goes from concave up to down, then here, here, and here. But if I drew a different graph, maybe I'll just get rid of this one briefly. If I drew a different graph, I'm just going to sketch something real quick that looked like this. And there's some sort of a vertical asymptote here. Notice that even though this goes from concave down, because our tangent lines are above the curve, or the curve is below our tangent lines, to concave up, because our tangent line is above or below the graph, and our graph is above the tangent line here. Even though it switches concavity, since it switches at an asymptote, that's not actually an inflection point. It has to be a point. So those are some things to look out for. All right, so what we know is concave up means the second derivative is positive. Concave down means the second derivative is negative. Inflection points are where that sign of the second derivative changes. And you might start recognizing some of this kind of thing, because if we start looking at some examples, we're really just going to be building some sign charts. So the process here is going to be very similar to what we did for the first derivative. We're just going to be naming things differently and interpreting things differently. So we're not going to be looking for critical points here. We still are going to look for partition numbers of the second derivative, and we're still going to check to make sure those partition numbers are in the domain to make sure that it's not like a vertical asymptote like this. But then we'll go ahead and fill out our sign chart, and we'll check the sign of the second derivative now instead of the first. And the way that we interpret that is not whether our function is increasing or decreasing, but that's going to tell us if our function is concave up or concave down. So it sounds really confusing, but I promise it's not too bad. The hardest part is going to be the interpretation, remembering what you're dealing with. So here we go. Here's an example. Here's our function. We're going to find the inflection points and the intervals of concavity, concave up and concave down here. Since we're talking about inflection points and concavity, we're going to try and associate that right away with the second derivative. So let's find the second derivative. The first derivative is 3x squared minus 12x plus 9, and without stopping, we're just going to blaze right on past that and say the second derivative is 6x minus 12. This is a pretty easy example, because now when we start looking for partition numbers, we're going to still look for where the second derivative is either equal to 0 or doesn't exist. And my guess is that by now, just by looking at this, if you haven't found it yet, pause it. But just by looking at this, you can see that the partition number is 2. There's only one. This is when the second derivative is equal to 0. So now we can go ahead and set up our sign chart. It's going to look very much the same as before. Maybe I'll just section this off with a little line here. All right, so here's our sign chart. We've got x values. They're going to go from negative infinity up to 2, and from 2 to infinity. One difference, when we pick out test numbers, we're going to check those in the second derivative because we want to check to see the intervals of concavity. We want to see what the sign of the second derivative is to see if it's concave up or down. So we'll pick maybe 0 and throw it into here. If you plug 0 into this, you get a negative. And maybe we could pick 3. If you plug 3 into this, you get 18 minus 12. That's going to be a positive. Now, instead of saying down and up, because we're dealing with the second derivative, we're going to say our function is concave down and then concave up. There are different symbols that you can use for this. So if you find something else that you'd like, some people draw parabolas on these or whatever, that's fine too. But notice that at 2, the second derivative we found was 0. Because of that partition number, we said, hey, f double prime of 2 is equal to 0. That means that at this spot, since our concavity changes, this is an inflection point. Now, the only thing we have to do is make sure that this x value of 2 is actually in the domain of our function, which it is. If you plug 2 into your function, you get a real number. So this is actually a point on the graph, so there's an inflection point here. It happens at 2 comma f of 2, which is really 2, let's see, if we plug 2 into this, we get 8 minus 24. I'm going to write this down because I'm going to forget. 8 minus 24 plus 18 plus 1. 8 minus 24 is negative 16, plus 18 is 2, plus 1 is 3. So we've got an inflection point at 2 comma 3. It's concave up on 2 comma infinity. And it's concave down from negative infinity to 2. Pretty cool. Not too bad. Let's check another example here just to see. This one's a little bit different. I'll maybe give you a second to see if you can find all your derivatives and stuff like that. You know you're going to need the first derivative. There's going to be some chain rule going on. And then the second derivative, it's going to be a little bit more annoying. So I'll fill this up with some work, and then we'll get rid of all that to save some space. Anyways, go find your derivatives here. Pause the video and see if you can figure it out. All right, so some chain rule should give you this. And then there's going to be a quotient rule. It's going to be super annoying to do. So let me just write it out really quickly. U is 2x minus 4. You know what? I'm just going to write u prime and v prime. I'll just call that u and v right here. There's my u. There's my v. U prime is 2. V prime is 2x minus 4. So now I've got to do vu prime. So I'll say 2x squared minus 8x plus 10 minus uv prime. That's 2x minus 4 squared. So that's going to be 4x squared minus 16x, but that's now going to be plus 16x because of that negative sign. And then it's going to be plus 16, but it's actually going to be minus 16 now because, again, the negative sign. Over v squared, so that's x squared minus 4x plus 5 squared. Ugh, this is annoying. So we've got negative 2x squared plus 8x plus 6 over x squared minus 4x plus 5 squared, or negative 2x squared minus 4x minus 3 over x squared minus 4x plus 5 squared. And we can factor this. Numbers that multiply to get negative 3 add to get negative 4. That's not going to work. Oh, I think I see what it is. I'm switched up a sign, so let me go fix that. 10 minus 16 should be negative 6. So that's positive, so that's going to make this easier to factor, because now we've got numbers that multiply to get positive 3, add to get negative 4. That's going to be x minus 3, x minus 1. Okay, so let me erase a bunch of this and get our regular derivative in here. I'm going to get rid of this stuff first. I want to get rid of that one too. Oh boy, where's my eraser? Here we go. And I'll copy that down, and then we should be good to go. So negative 2 times x minus 3 times x minus 1 over x squared minus 4x plus 5 squared. Let me get rid of everything else so we have some more room. Okay, so there's our second derivative. We need now partition numbers. Notice at the bottom, I don't think can be factored, right? Numbers that multiply to get 5 and add to get negative 4. No. And if you plug in anything, what you'll notice is that this is always going to end up being positive inside of here. It'll never actually equal 0. So the nice part of that is that there are no x values that will make the denominator 0, meaning there are no x values that will make the second derivative not exist. So we only have to worry about these two partition numbers, 1 and 3. So for our sign chart now, let me clear this out the way. We're going to have a couple of intervals. We're going to go from negative infinity up to 1. We're going to go from 1 to 3, and 3 up to infinity. And these are all of our x values. We're going to check the sign of these in the second derivative here. So go ahead and fill out your sign chart, see what you get, and then we'll come back and test things. All right, you should end up with something that looks a bit like this. So now we can see on our function, this negative is really concave down, this positive is really concave up, and the negative is really concave down. So you've got two intervals where it's concave down, one interval where it's concave up, and your inflection points, you've got two of them. There's one here at 1, f of 1, and there's another one at 3, f of 3. I'm not going to figure out what those y values are. I don't really care, to be honest. But you would go ahead and do this. And just to save time, I'm not going to. But you could plug all the 1 and the 3 back into your function to find those y values and get the actual inflection points on here. All right, so why do we care about this? Well, there's lots of different reasons. But since this is a business calculus class, I want to show off a quick kind of little business application. It's based on diminishing returns. So let me write this up here. Diminishing returns is probably something that you've heard of if you've taken some economics classes before. A lot of people that take this class have been through at least one semester of like microeconomics or macroeconomics, depending on the order that you take them in and what school you're at and blah, blah, blah. But in some economics class, somewhere in your history, probably at least half of you have heard of diminishing returns before. This is the story I like to tell about diminishing returns to try and illustrate it, to try and remind us of what it means. When I was an undergrad, I was in my school's cafeteria because I was living on campus, and especially my freshman year, I found that I didn't like a lot of the food options that there were. And so instead of like trying my luck on any of them, what I would do every day is go eat at the sandwich cart. There was a sandwich cart in our cafeteria, so there was a person with different lunch meats and lettuce and vegetables and things like that and different types of breads, and you could make your sandwich and go from there. So that's what I did. I ate sandwiches every day. And after the first semester of eating sandwiches almost every day, you could imagine that I pretty much started hating sandwiches. So this is the idea of diminishing returns, that if you do something over and over and over again, you're going to eventually get less and less and less good out of it. Now, in my example, I ended up getting like a negative feeling about sandwiches. I had to go off sandwiches for a whole semester just to try and kind of make up for the fact that I didn't really have that good experience with sandwiches. So that was something that was kind of a weird thing that I had to keep out for. But that doesn't always happen. We can get positive feedback or positive value from doing something, even though it's just less positive value. The first time you do something, or the first few times you do something, you get a lot of positive value out of it. But as you keep going, it starts losing value, even though it could still be positive. Anyways, let me show you what I mean here. Let's pretend that we've got this discount appliance store. I think that's supposed to say appliance instead of application. Oh, well. It's selling 200 large screen TVs monthly. What we're going to do for this store is we're going to start by investing some money into an advertising campaign. X is going to be in thousands. So down here in this interval, this is really $9,000. So they're going to invest some money into an advertising campaign. Obviously, we hope that when we invest money in the advertised campaign, our sales are going to increase. Hopefully, we don't ever get negative value out of this, where the sales decrease. But we might imagine that sometime our sales will increase less than they used to. So we want to find that point of diminishing returns. And the way that we can do that is by messing around with some derivatives. So we'll take a look at the first derivative of this, and we'll say that's going to be 9x squared minus x cubed. And if you want, we can try and make sure that our sales are actually going to be increasing. Let's factor this. And you'll notice we've got two partition numbers, 0 and 9. Those are the endpoints of our function. So we just need to check between 0 and 9 to make sure that n prime is going to be positive. Let's plug in 1 and see what happens. If you plug in 1, we get 9 minus 1. That sure is positive. That means that our function is increasing the whole time. That's good. If our function was decreasing, that would mean that if we put in a certain amount of money into this advertising campaign, we'd actually be losing sales. That would be a terrible campaign. So it's good to just double check this part. So it is increasing the whole time. What we want to do now is check out the point of diminishing returns. Oh, I should have kept up that first derivative because we'll need the second. Oh, well. Let's just go quickly. The first derivative is 9x squared minus x cubed. So the second derivative then is going to be 18x minus 3x squared. And again, we can factor this to make finding those partition numbers a little bit easier. And we can say this is going to be 3x times 6 minus x. And again, we've got some partition numbers here, 0 and 6. So what we want to do is build our sign chart from, I'm going to start at 0 instead of negative infinity because that's our domain from 0 up to 9. So I'm going to go from 0 up to 6 and then from 6 to 9. These are our x values, and I want to check the sign of my second derivative. Here, if we plug in a number like 1 from this interval into our second derivative, we get 18 minus 3. That's going to be positive. And if we plug in a number like 7, we're going to get, let me plug that in here, 21 times negative 1 if we do 6 minus 7. So that's going to be negative 21. All we care about is that it's negative. That means our function goes from concave up to concave down, and we've got an inflection point at x equals 6. So that's something to just keep an eye out for. So think about that inflection point a little bit. When we sketch things, though, we might notice that that inflection point visually will look like this point of diminishing returns. So I'm just going to give a quick sketch of our graph. Let me draw some axes up here. There. This is going to be not a very accurate sketch, but oh well. I'm just going to go ahead and say 3, 6, 9. And I'm going to sketch the graph from 0 up to 9. We know that the function is increasing the whole time, because we found that it was increasing the whole time, but also we wanted to make sure it was, or else this is a terrible advertising campaign. So that means when I draw my graph, I'm going to be moving up like this the whole time. But to start, I'm going to be concave up, and then I'm going to switch to concave down at this inflection point. So maybe I'll just kind of plot the inflection point here. So I'm going to start with it being concave up here. Wait 1 sec. Oh, it was a closed point. I was just checking the domain to see if we included 0 or not. I'm going to start with it concave up like that. See how I've got some upward concavity? I'm going to switch to concave down at the end. So this point here is the point of diminishing returns. As we increase our money, our advertising campaign, our sales do increase. They go up, but eventually not by much. If we look at the difference between this point and this point, there's a pretty big jump in money. This is maybe like $1,000 or $1,500 jumped up in money, but there's not a huge increase in our sales here. So this is that most efficient point, I guess you could say, or the point of diminishing returns, but really it's the inflection point. It's where the curvature of our graph changes a bit. So there's an application of this for you, just to kind of see. But mess around with the second derivative. There are lots of different examples that you can look at. And the nice thing about here is that we're going to get some practice on our derivative rules as well. Because as you could see in the second example, we had to do some chain rule, some quotient rule, things like that. We're going to be having to find derivatives consistently. So make sure that you are up to snuff on all those differentiation rules. Good luck, and let me know if you have any questions.